This is a lesson on absolute value functions in a precalculus course. Absolute value functions encapsulate the toolkit function of absolute value x. I'm going to remind you that we know about transformations and we're able to transform x according to however we want to shift it left or right, up or down, or make it stretched or compressed or shorter or taller, right? And what I'm going to tell you is that an absolute value function is a special case of a piecewise function, where there's a certain value for one part of the graph and there's a certain function for another part of the graph. Certain function here, certain function here. So again, when we look at graphs of absolute value functions, because they're kind of like piecewise functions, we have to think about the domain. What part of the function is relevant on what part of the domain? One of the learning objectives I have for this lesson for you is, of course, to graph absolute value functions. So if you were given a function of this form, would you be able to graph it? So I think that's pretty straightforward. Find the vertex and then you can look at the slope. That's not too bad. I don't think that's too bad. What I see students struggle with is writing the absolute value equation given a graph. And I can see how that can be as frustrating as writing piecewise functions in the last lesson I did. So this example that I have here, it says write the function shown as both an absolute value function and a piecewise function. Well, I am going to do, of course, part A first, right? That's what you're supposed to do. And what I'm going to remember is that when we're working with piecewise functions or any function in general and we have some transformations, I'm going to take the original form of the function and add in my transformation terms in there, the a, b, and c. So I need to identify a, b, and c for this problem. Vertex for the absolute value function usually starts at the origin. What I'm going to note is that the vertex has been moved over 4 in the x direction and down 3 in the y direction. All right, so when I do that, I'm going to notice b is a positive 4 and c is a negative 3. Another thing I'm going to notice is that a regular absolute value function, right, just absolute value x, has a slope of 1. So if I drew the original function on the graph, it has a slope of 1. So it looks something like this, slope of 1. And this, you can see, is a little bit steeper than that. So the trick here to do, and I think this is pretty clever, is to do our rise over run. Okay, and I'm going to work on the positive part of this graph over here. I'm going to do rise over run. Here's a point here. If I rise 2, I go over 1. So I have a plus 2 and a plus 1, which gives me a slope of 2. And that is going to tell me m equals 2, so that means a equals 2. So pretty straightforward and quickly on, just write the absolute value function using transformations, reading the graph. I'm going to say 2 absolute value of x minus 4 minus 3. Done. Okay. So that's the first part of that problem, and I don't think that's a hard part of the problem. The part of the problem that I see students struggle with is the second part here, where it wants the piecewise function. And there's a trick here for you to remember how to do this. All right, so we see that we have 2x minus 4 minus 3. So I'm going to divide this into 2 different parts. What you're going to notice is there's this line of symmetry that we have, right? This point where the vertex, it switches. We have some of the domain on one side, some of the domain on the other side. So when I'm filling in the domain part of my piecewise function, I'm going to identify that line. All right, and so the standard thing to do for a piecewise function is to say that the first part is x less than that line of symmetry value. It's 4 in this case, right? And then the other part is greater than or equal to that. So that's the domain. Let's work on the functions during that. The trick about absolute value, and you may remember this from classes that you've had, including absolute value before this point, is that when we take those absolute value signs off, we need to consider a positive value for it and a negative value for it. So I'm going to divide this up into 2 different parts of that line where I know this is true. 2x minus 4 minus 3. and then 2 negative x plus 4 minus 3. Do you see how what was in the absolute value is now in parentheses, and I have a plus version of it and I have a minus version of it. So we're going to divide that piecewise function up into its two different pieces. I'm going to note that this side here, this left side, it definitely has a slope of -2. So this is the left side of the graph. This one here, this is the left side of the graph, and this is the right side of the graph. I'm going to simplify this into a line, just an mx plus b for each portion. So which means I'm just going to do some algebraic simplification here. I'm going to distribute the 2x minus 8 minus 3. So I'm going to get 2x minus 11. And if we follow this back here, I guess it probably, intersects at -11. So that's the first part of the graph. Or I'll say that's the left part of the graph, with L meaning left there. The function on the right side of the graph, I'm going to do the same thing. I'm going to distribute that 2, so I get -2x plus 8 minus 3. I'm already doing math in my head, you may have noticed, so -2x plus 5. And we can see that the intercept for that portion of the graph is a plus 5, and it has a slope of -2, so that's the function on the right side of the graph in terms of x. When you fill this in up here, you're going to fill in, what do we get? Negative, did I leave the negative off? -2x plus 5 for the left part of the graph, and then a positive 2x minus 11 for the left part of, or for the right part of the graph. Okay, so that's how you divide that up. We're going to keep a hold of that trick of basically taking apart the absolute value. When I look at an absolute value, I have two possible situations. I take the absolute value of a positive of whatever the number is, or I take the absolute value of the negative of whatever that number is, and I get the same thing. So that's why there's a positive portion of solving and there's a negative portion of solving. So let's solve some absolute value equations and functions. I'm going to have you start thinking about solving these in regard to functions, solving absolute value equations in terms of absolute value functions. What I'm going to note is that we're going to set the absolute value of an expression equal to another value or expression. It could be, where does, to a parabola, we'll look at an example where a parabola and an absolute value function meets, right? We can have more than just lines there. So it could be any function or expression equal to an absolute value. We need to consider, like I said on the previous slide, both the positive and negative solution. We're going to note that there's two solutions here. When this line intersects the absolute value, I have two solutions. So even though when I write this out, it looks like there's going to be one solution, I need to solve for two solutions. So we're going to solve for the two different equations. We're going to solve two different equations independently, and we're going to look at the graph to verify the algebraic solutions. I know it may be just easy for you to say, well, I'm just going to graph it. And that's fine. I would like you to verify your solution that way, but definitely if you're doing work for me, I want to see the algebraic solving the equation using algebra, right? Algebraic techniques. So the example I have here, it says if f of x is 2x minus 6 and g of x equals 8, when is this function equal to this function? Well, I already marked those points on the graph. Let's solve with algebra. Guys, I'm going to pull out a 2 from that absolute value. If I bring a 2 out from that absolute value, 2 absolute value x minus 3, and then I'm going to set that equal to 8, right? I'm just solving for when one function equals to another. I'm going to put an equal sign there. And that's going to jive with what I see on the graph, where I see the vertex of this absolute value function at 3, right? That's 3. Okay. So what we're going to do is we're going to get the absolute value by itself on one side and everything else on the other, which is pretty easy in this situation. I'm just going to divide by 2, so I get absolute value of x minus 3 equals 4. I'm going to divide this up into two solutions. All right. I'm going to have the positive solution and I'm going to have the negative solution. The positive solution says I'm going to take whatever's in the absolute value and equal to whatever is on the other side. I'm not changing anything. I'm just taking those absolute values away. The other one is I'm going to take whatever's in those absolute values and equal it to the negative of what's on the other side. So I get a -4. So one value I get x equals 7, the other value I get x equals -1. And like I mentioned, you're going to solve algebraically. There's my algebraic solutions. I set up equations and solved with algebra for my solutions. And what you're going to know is there's the -1 solution and there is the +7 solution. Okay, those are where it intersects. And what I wanted to really note about making the graph for solving is I do believe I broke this problem into parts. I separated f of x away from g of x. I do believe this original problem was set up like this and said solve, just solve it. So I turned it into function form for you all. And what you're going to note is I did not graph this thing. I graphed this part of the expression, this part of the equation I graphed, and this part of the equation I graphed. I graphed each of those separately. They're two different functions. And then when I solve, I can identify these points of intersection for those two functions. Okay, if you plug this equation in like Desmos, what you're going to get is just a number line, and you're going to get a line here and a line here, just indicating those are the solutions. What you're not going to see is the shape of the absolute value function and that line. You're not going to see the red and blue that I have on that picture there, which I don't think really represents a full mastery or understanding of what we're doing when we solve this absolute value is equal to another value, right? So when you graph this, I want to see the red and blue lines on here, not just what are the answers. Let's do another complicated thing that can be intimidating for students. Also in this lesson is solving absolute value inequalities. All right, so before it was an equality and we're actually solving for actual values. But if we're solving inequalities, we're going to provide a range of values that satisfies an expression. So I'm going to show you this to you on a graph, and then I'm going to help you solve algebraically because you may have seen this before, but a lot of students still struggle with this, and I want to make sure that you know how to do it as you move through pre-calculus heading towards calculus ideally. Okay, so what happens is, and you may remember this, these rules if you've seen this before, is that if there's a less than, you're going to have a single interval for solutions, a less than or equal to. If you have a greater than or equal to, you're going to have two different, a union of intervals, I'm calling it, a union of intervals you're going to have. And also, you'll get creeped out, but you'll be able to watch out for it, is that sometimes there's going to be all values are true or a solution does not exist. So there's 4 different options that when you're solving absolute value functions inequalities you could possibly get. So I'm going to run a little bit of gamut here so you can see a couple of them and know how to recognize them. What I have down here is, of course, our answer from our problem from before. I didn't want to change it. Like, we're already familiar with what's going on. We already solved, right? We have a -1 here and we have a 7 here. All right. And so just graphically, when I look at this, it says, when is f of x, we'll just do the first one here. When is f of x less than g of x? Okay, so f of x is the absolute value function. And we want to know the domain over which the absolute value function, the output of the absolute value function, is less than 8. Well, looking at the graph, I'm going to notice that's in this portion here, and that's in this portion here, right? Actually, it's one whole portion from here to here, from -1 to 7. I'm going to note that the red line is below the blue line, right? The output of the absolute value function is less than 8. I'm going to use a less than sign because it just says less than. So from -1, less than x, less than 7, we know that the absolute value is less than 8. If we look at the second part here, when is the absolute value greater than 8? All right, so what we're going to notice is that here's this line 8. For any value of x less than -1 or greater than 7, we're going to have that absolute value greater than 8. So you're seeing how I'm exemplifying a single interval. This is a single interval. Do you all see that? It's less than. We're using the less than, as opposed to two different intervals, a union of intervals with the greater than. I'm going to write down x less than -1. Or if we're doing interval notation, I guess I'll go from -infinity up to -1, and I'm going to union it. There's a union of intervals, right? X greater than 7, so that'll be 7 up to positive infinity, and I'm using parentheses here because there is no equal sign in my inequality. Okay, so I like the graph, like starting on the graph with absolute value inequalities. We know how to graph functions, and then we know kind of how to look at a graph and say, at what point is one function above the other? At what point is the function below the other? That's how I think about it. Let's incorporate some algebra, though. I know you all want to see some algebra, and so let's do something a little bit more complicated here. I'm calling this a standard solution. This is just a standard solution. There's nothing like weird going on. You should be able to calculate some numbers, and it'll either be a single interval or it will be a union of intervals. It says solve the inequality, write the solution using interval notation, express all values as integers or reduced fractions. So that means no decimals, okay? No decimals. Integers or no decimals. Enter D and E if no solution exists. Oh no. So like I said, there's 4 different options. We could have a single interval, a union of intervals, infinite solutions, or no solutions. So this is a standard solution. I'm not going to make it so that there's a DNE or an infinite number of solutions. Let's just work through this. So algebraically, what do I need to go on here? What is going on here? What my tip is to isolate the absolute value on one side and everything else on the other. So what I'm going to do is I'm going to move that 3 over to the other side. I do math in my head apparently while I'm writing. So I'm going to say that -4 absolute value 7x plus 8 equals, is greater than or equal to -5. I'm just moving that 3 over to the other side. I will say at this point, I see students struggle with knowing how to solve this algebraically, which is why I'm going over it, just to remind you, refresh you, or give you some really good direct instruction about how to solve absolute value inequalities when you have some complicated stuff going on here. All right, we're going to use our regular rules for isolating a variable. We're just going to pretend like this is its own variable. I'm going to shoot for getting this on one side and everything else on the other, which means I can't do the -4 first. I need to deal with the -3. I'm going to add 3 on both sides. That gives me -5 on that side. In order to get -4 out of the way, I'm going to divide by -4. I'm going to notice because I'm dividing by a negative. All right, when I divide by a negative with inequalities, I need to switch the direction of that inequality. So I'm going to get absolute value of 7x plus 8 is less than or equal to 5/4. Okay, so that's switched. Because of that negative sign, I'm switching the direction of that inequality. So this is the form that I was going for. I have the absolute value by itself on one side and then everything else on the other, which just happens to be a number in this situation. So I'm going to divide this up into 2 solutions. Remember, when I'm doing this, I'm going to have 2 solutions. I'm going to positive solution and the negative solution. So the positive solution, I'm going to write that down just as it is. I'm not changing anything other than taking the absolute values away. So 7x plus 8 is less than or equal to 5/4. The other one, I'm going to change the direction of that inequality, and I'm going to make a negative sign on the other side. So I'm going to keep the 7x plus 8. I'm going to change the direction of the inequality, and then I'm going to make this negative 5/4. It can be less than 5/4 or greater than negative 5/4. And if that's making sense in your head, it seems to me that we're going to have a single region on that graph where that is going to be a true statement. Let's solve for those values. I told you I need you to be able to do this algebraically, so let's solve algebraically. So I need to subtract 8 here and subtract 8 here. 8 is 32/4, so 5 minus 32 is negative 27. So I get 7x is less than or equal to negative 27/4. So x is less than or equal to negative 27 over 28. Which is almost 1, right? Almost negative 1. So x has to be less than that. Let's go to the other solution. I'm going to move a negative 8 over to the other side again. So I get 7x, but I have a negative 5/4 over on that side. So I'm going to be taking negative 5 and subtracting 32, which results in a negative 37 over 4. And then I'm going to divide each side by 7, so I get negative 37 over 28, which is a little bit greater than 1, which is looking about right. I'm going to have a lower bound of negative. It seems like, it's in the wrong direction, but I'm going to have a lower bound of a little bit over 1 and an upper bound of a little bit under 1, and so that will be true, and which is looking about right. I'm going to have a lower bound of negative. It seems like, it's in the wrong direction, but I'm going to have a lower bound of a little bit over 1 and an upper bound of a little bit under 1. And so that will be true. And so when I write this out, I know that I'm going to have a single interval with a lower bound and a higher bound, and I always go from lowest number to highest number. So on the number line, the negative 37/28 is the lowest number, negative 37/28, and the highest number is negative 27 over 28. That one's closer to 0. So that would be my solution. But I have a feeling that it may not be as apparent to you solving algebraically that's going to be a single interval as opposed to two different intervals, right? It could be like this part of the graph and that part of the graph and not in between. So I do encourage you to graph them. What I want you to do when you do this is graph one side of the inequality separate from the other side. So like I can call negative 8 g of x, and then I can call the other side maybe f of x, whatever you want to call it, h of x, whatever you want to call it, f of x. I called it f of x. So when I graph those two functions, I'm going to note that what I solve for here is their two intersection points, right? So this will be over 1. You can see it's over 1, so negative 37/28. And this is a little bit less than 1. This is the negative 27/28. And what the question asks for is when is that absolute value function greater than that line? And we can see it on here, right here. Just the peaky portion of the absolute value is when the absolute value is greater than negative 8. And you can see that that would be in this region in here. And so when you're identifying these regions, what you're going to see, especially if you're using Desmos and you're asking it to help you find solutions, is that we're going to shade that area. And what happens is the shading will be just between those x values. So it might seem like you only need to shade like this portion, which I don't think I would necessarily mark you wrong for that, but technically you're supposed to shade the graph like this. Between those two values is where this inequality is true. Okay, so that's what you're solving for. That's a standard solution. So we did an example with a union on the first slide that I showed you. We did an example here with just a single interval, and I wanted to show you what a weird solution looks like. And you can see here that it looks very similar to our previous example, right? It looks like I can just solve like I normally did on the previous example. And let's go ahead and do that. Very similarly, I'm going to add a 6 on both sides, so I'm going to get -7, absolute value 6x plus 6 is greater than or equal to 12, all right? Then I'm going to divide, right? I need to divide by -7, so I'll keep the absolute value of 6x plus 6. I'm dividing by a negative, so I'm going to switch the direction of my inequality, and so I'll get -12/7. Okay, so now I'm ready to split this up into its two solutions here. I'm going to have a positive solution and a negative solution. And I don't think there's anything funky going on here necessarily. When is the absolute value less than or equal to -12/7? It could be that you're already keen on this. I'm already going to tell you to graph these two functions separately. I'm already going to tell you to let one equal g of x. I'm already going to tell you to let one equal f of x, and then graph those two functions. Which may feel like I'm giving the answer away. There it is. Do you see how that's a weird solution? When I look at this graph, there's no intersection points. This line, +6, never intersects this absolute value. And it asks, when is the absolute value greater than 6? It's asking when is the absolute value greater than 6? It's not, ever. So this is a situation where there's a DNE. This is a does not exist answer. Okay, I think this can sneak up on you if you're not graphing. If you are not graphing these functions, you might get your numerical answers and pull your hair out. Why is my answer not entering? Why is the computer not accepting my answer? Let me show you. I'm going to explore this a little bit more. I'm going to keep solving this with the positive and negative solutions and show you why you get some numerical answers that aren't relevant, that you just kind of toss out. We call these extraneous solutions. All right, so I'm going to solve like I did on the previous problem. I'm going to take the positive version of this. So I'm going to take 6x plus 6 less than or equal to -12/7. I'm also going to take the negative version of this, 6x plus 6. I'm going to switch the directionality, greater than or equal to +12/7. Remember, I changed that inequality direction and I changed the sign. So I'm going to solve here. I'm going to subtract 6 on both sides. I'm going to note that 6 is 42/7, so I get -12 minus 42/7, so I get 6x is less than or equal to, what is that? 42 plus 12 is -54/7, and so I get x less than or equal to -54/42. I get a numerical answer. I get a solution that satisfies the positive part of this solution, right? The solution strategy. Let's look at this on the number line on our graph though. -54/42, that's a little bit greater than -1, right? I'm going to say that's a little bit greater than -1. Why am I getting this intersecting at a little bit less than -1 when it does not? Well, what I'm going to show you is that on this positive part of the function, you're going to know when I extend it upward and it never goes there, I am getting an intersection point with that line. And that's what this is solving for, is for a point that doesn't exist because it's considering the other half of this line, which is not part of the absolute value function. So I think that's kind of creepy that you're going to get a numerical answer and try to interpret it, and without the graph, you're going to get pretty confused. So the absolute value never intersects the line at that point. I'll also tell you that the absolute value does not intersect the line at the other point. What, 6x greater than or equal to +12 minus 42 is -30/7. So x is greater than or equal to negative 30 over 42, whatever that is. It's less than 1, right? And I can notice that would be the extension of this line back here. It never actually goes there, but it is a numerical solution. So when you're doing this stuff, more and more you're seeing the utility of graphing the functions. When I look at that graph, that's going to tell me so much more than what's going on in that algebra, and these two should verify each other. I think this is a situation, again, where it can get confusing, where you're actually getting numerical values, but they're not for a real portion of the absolute value graph. Those are actually not portions of the absolute value graph. They're not on the graph. So there cannot be an intersection, and so that's why we're getting this DNE as an answer. The last problem I have for you here is graphing absolute value inequalities, where you have a system of inequalities. Okay, and in your homework, I do believe it just says graph. I put in here solve algebraically. Like I said, I wanted to be this little bit more algebraic review for you as you're solving for these, and lay the foundation for solving other inequalities as we move forward in the course. So solve algebraically and then graph the solution. It may be that you just pull the trigger and you graph the solution. I have a parabola. With an HK of 1, 1. So it's moved over 1 and up 1, and it's a parabola. So I could even draw that on here, right? There's the vertex, and then I know how a parabola grows. It grows 1 over 1, and then 2 over the next one. Hopefully you remember this from your last class. And then I'm just going to draw this rough parabola in here. I'm going to do it a little bit better because I need to have a certain portion of the graph accurate. So that's our parabola. So I'm doing part B first as opposed to part A. Let's draw the absolute value in here. Its vertex is going to be at 2, 2. Okay, I can do 2, 2. And I'm going to note it has a slope of negative 1. So it's going to be pointing downward, and it's going to have a slope of 1. Okay, so there's 2, 2, and it's going to have a slope of 1. I'm just going to keep extending this off the graph close enough, and then a slope of 1 here off the graph. Okay, so there's the absolute value. And what they're asking for is all values that are greater than the parabola and less than the absolute value. For what part of the domain is the output of the one greater than the output of the other? Okay, so when I look at this, I can do this as well, and I'm just going to use some highlighter here to highlight it. The first part says the output is greater than the parabola. That's how I'm going to read that. The output is greater than the parabola. Well, that's going to be in this region here. When the output is greater than the parabola, it's all of this region in here, all the way down there. You can see that overlapping region in there. That's going to be a region of interest, right? And then the other portion of this piecewise, it's a piecewise. You can see the piecewise inequality. It says when is the output less than the absolute value? So I'm going to go on this less than side, the bottom part of this absolute value. So that's all of this region. So when you're graphing, make sure you're shading accurately, all right? And we're going to see the solution here. This is the solution right there. What could I mark it with? Yellow? Maybe a yellow will be okay. Maybe you can see the yellow in here, all right? This little portion in here, from here to here. That purple portion that I drew, that the blue and the pink overlap, that's going to be our solution. Let's solve for it algebraically. I know you're dying to see how I solve for this algebraically. What I'm going to do is I'm going to solve for these two intersection points. I can read them off the graph, but we need to be able to solve algebraically. So what I'm going to do is just set these two functions equal to each other. I already know that there's an interval in there that I'm really interested in. It's not the outside of it, it's the inside. So I want a single interval, and so I want to solve for those values algebraically. For what part of the domain is the output of the one greater than the output of the other? Okay, so when I look at this, I can do this as well, and I'm just going to use some highlighter here to highlight it. The first part says the output is greater than the parabola. That's how I'm going to read that. The output is greater than the parabola. Well, that's going to be in this region here. When the output is greater than the parabola, it's all of this region in here, all the way down there. You can see that overlapping region in there. That's going to be a region of interest, right? And then the other portion of this piecewise, it's a piecewise. You can see the piecewise inequality. It says, when is the output less than the absolute value? So I'm going to go on this less than side, the bottom part of this absolute value. So that's all of this region. So when you're graphing, make sure you're shading accurately, all right? And we're going to see the solution here. This is the solution right there. What could I mark it with? Yellow? Maybe a yellow will be okay. Maybe you can see the yellow in here, all right? This little portion in here, from here to here. That purple portion that I drew, that the blue and the pink overlap, that's going to be our solution. Let's solve for it algebraically. I know you're dying to see how I solve for this algebraically. What I'm going to do is I'm going to solve for these two intersection points. I can read them off the graph, but we need to be able to solve algebraically. So what I'm going to do is just set these two functions equal to each other. I already know that there's an interval in there that I'm really interested in. It's not the outside of it, it's the inside. So I want a single interval, and so I want to solve for those values algebraically. So what I'm going to do is take the absolute value plus 2 and just set it equal to this parabola. Okay, that's pretty easy. I can do that. Another thing I want to do is isolate the absolute value on one side and everything else on the other. So that means I need to subtract 2 on this side. Let's subtract 2. So I have negative absolute value of x minus 2 equals let's go ahead and expand this. I really want to expand this. X squared minus 2x plus 1 minus 1. So, I have some cool stuff going on. Those ones cancel. And then in order to isolate the absolute value, I'm still going to multiply by a negative 1 on each side. Negative x squared plus 2x. Okay, so now we can expand that absolute value out into its positive solution and a negative solution. This is kind of cool. I like this problem. We're going to have a quadratic here, so I'm laying some foundation for some review material that we're going to move into next with quadratics with factoring. So if I write out the positive equation for here, I'm just going to keep whatever's in the absolute value, and I'm just going to keep whatever's on the other side, and I'm just going to write that without the absolute value sign in there. So that has to be true. The negative solution is going to be whatever's in the absolute value, multiply, and on the other side, we're going to take the negative of that. So x squared minus 2x. So let's simplify this. Let's get a quadratic on one side and 0 on the other. I'm going to put a 0 on the right side and everything else on the left. So I'm going to get x squared minus 1x minus 2. All right, you can check my algebra. I'm very confident on that. I'm going to put the 0 on the left side. I like shooting for having a positive x, whatever the highest power is. So that's why I move this over to this side. I'm going to leave this guy over on this side. X squared, I move an x over, I'm going to get a minus 3x, and I move this 2 over, I'm going to get a plus 2 there. And if you remember factoring, you may see it. I'm going to have an x minus 2 times an x plus 1 here. And I'm going to have an x minus 2 and an x minus 1 on this one. So overall, I get x equals 2, x equals minus 1, x equals 2, x equals 1. We have an extraneous solution. This negative 1 here, that's not a solution. We can see that on the graph. We have 1 and 2. So the 2 makes sense and the 1 makes sense. I'm not sure what was going on with the negative 1. I think it's when it extends back here and it intersects back here, right? I think that's where it intersects. And that's why we're getting this extraneous solution. And so you can see that's how I would solve this absolute value inequality, the system of absolute value inequalities. And again, we can write out the solution. I'm going to write out the solution. It can equal those values. No, it can't equal those values. So I'm going to note at this point, because it can't equal those values, I needed to do something with that black line. That black line that I drew for the parabola isn't actually accurate. So I apologize for that. I'm going to get rid of that there. I'm not going to get rid of I'm going to try not to get rid of the highlighting. Because it's a not equals, I have to put a dotted line in here. So I'm going to put a dotted line in here. There we go. And, because it can't equal, I think I would do an interval of 1, 2 where it's not equal to those. Hopefully that's clarified how to solve some absolute value just equations or inequalities. And again, draw the graph. Get that graph out, look at the graph, have your graph make sense with your algebraic solution, and be sure you're putting your algebraic solution in with your work.